Good morning, students. Anxious learners all, I know. So today's lesson, today's lab, second video lab we're doing this semester, is all about solenoids. We have different kinds of solenoids. We have vacuum control solenoids. They can control the flow of air, basically. Fluid control. They can control engine oil, transmission fluid, gasoline, diesel. And we have mechanical solenoids that can do things like pop your fuel door, trunk release, anything that needs to physically move. So the first thing we're going to do is we're going to look at some of the solenoids on the bench. Just kind of show them to you. I'll hook a couple up. We'll do a vacuum solenoid, see how it switches vacuum on and off. Then we'll mess around with a fuel injector a little bit. Just going to use water. Maybe someday it would be fun to try it with gas and a flame, but I don't think so. And after that, we'll move out in the shop. And in the shop, I'm going to show you how solenoids are sometimes controlled. They're not always just on and off. Sometimes they're controlled so that they're more on or more off, or on longer so there's more flow through them. We have two methods. One is called duty cycle, the other is called pulse width modulation. We'll look at both. Then we'll actually watch a fuel injector pulse coming from the computer. We'll look at that with a light, and then we'll look at it with an oscilloscope. After that, I'll come back in and we'll kind of wrap things up and let you know what you need to do for your report. On the table I have several different kinds of solenoids. So this one here is kind of old. It's an old idle air control valve. The throttle plate on the throttle body would be right between these two ports. So rather than open the throttle plate to increase the idle speed, this solenoid opened a passage from outside of the engine, in front of the throttle plate, through to the back of the throttle plate to let air in to increase the idle speed. Fuel injector, we'll talk about later in a little bit more detail. Here we have a variable cam timing cam phaser solenoid. So this is controlling the flow of oil into the cam phaser. But here's another kind that doesn't control fluid at all. This is a vacuum control solenoid. And a lot of times they're called solenoid valves, all of these. So a vacuum control solenoid either allows vacuum to something when it's energized or blocks the vacuum when it's energized. So I have here a vacuum pump. And with this vacuum pump, I'm going to connect it to the solenoid, and I should be able to pull a vacuum, look on the right way, pull a vacuum on that valve. So you can see it's gone down to about 20 inches of mercury until I hit the release. And it's holding that vacuum. This solenoid right now is not energized. There's no electrical connection to it. So next, I'm going to take a couple of jumper wires and I'll hook from battery positive on my jump box here to one of my electrical connectors on the solenoid, and battery negative to the other electrical connector. We'll pull that vacuum level again. And now I'll turn the switch on to my power supply. And you see what happens. As soon as the solenoid is energized, the vacuum goes away. So if I turn the switch off, give it a second, I can pump this back up. And it holds vacuum as long as I don't energize the solenoid. As soon as I flip that switch on again, you see the vacuum goes away. So this is what would be known as a normally closed solenoid. So what does normally closed mean? normal is the way it is when there's no power applied to it. So if this is closed with no power applied, so right now it's closed, I've taken the wires off, it's closed, that's considered normally closed. If this only held vacuum when it was energized, then it would be known as a normally open solenoid, and we would have to energize it in order to get it to hold that vacuum. So these sorts of solenoids are used to control vacuum to various devices, EGR valves in the old days. It could be controlling vacuum to something in the AC and heat system, to move a door if it's not an electronic system, all kinds of different applications for vacuum control solenoids. And they come in both varieties, like I said, normally open, which means they're open until you energize it, and normally closed, which means closed until you energize it. So which kind was this again? When I'm unhooked, I have no electricity to it. Is it open or is it closed? So what's its normal state without being powered up? So here's one example of a liquid control solenoid. This is a typical fuel injector, and if we look at it, we have the inlet where pressurized fuel comes in from the fuel pump. The electrical connector here, a little difficult to see, I suppose. 2 pins there. The outlet here that's directed either into the combustion chamber on direct inject or into the intake manifold on a port fuel injection system. So what I'm going to do is I'm going to hook this up to a source of pressure. We're not going to use gasoline, even though that might be more exciting. And we'll operate the injector and watch what happens when we apply power to it. In order to do our demo, we need a source of pressurized fluid. Now in the car, that would normally be the fuel pump providing pressurized gasoline to the fuel injector. However, since we're doing this on the bench, I needed to come up with another way to provide pressurized fluid. So I got this pump sprayer. Allows me to pump up, fill it with water, pump up some pressure, and then supply that to the fuel injector. So we'll use that for our pressurized fluid. I'll just connect a hose from this to the fuel injector. And of course we have the the 12-volt power supply. We're going to use that to energize the injector. And we'll see what happens when we apply pressurized fluid to it and then apply 12 volts to the terminals and watch the injector open and close. So here I have my pump sprayer. I have the hose connected to the input of my fuel injector here. Let's try to focus that in a little bit better. Nope, not gonna. And so I've pressurized it. I have pressurized water available at the inlet to the fuel injector. So what we'll do now, I have that hooked up to my 12-volt power supply, and when I turn that power supply on, we should be able to see something come out of that injector. I have everything set. I have my pressurized hose hooked up to the inlet of my injector. I have my power supply connected to the electrical connectors on the injector. And I'm just ready to turn that on. We're going to see if we can observe any flow out the end of the injector there. I put a little bit of water in the bottom of the pan. Hopefully this injector will create some waves and make it a little bit easier to see. So let's turn it on and see what happens. And turn it off. And back on. And back off. So you can see when you energize the injector, it opens the valve, and the gasoline, normally, in this case it's water, that's supplied to the inlet of the injector, comes out the outlet, sprays into the intake manifold, or on newer injectors, of course, directly into the combustion chamber. Years ago, a lot of vehicles had injectors mounted outside of the intake manifold, throttle body injection. But the concept is the same. The injector is a liquid control solenoid. When it's energized, it's a normally closed solenoid, so when it's energized, like so, it begins to flow, and when you take the power away, it shuts, and there's no more flow. Not all solenoids just turn on and off. This is the EGR vacuum regulator, which controls the vacuum to the EGR valve. And the EGR valve, instead of being just completely closed or completely open, can be controlled by the computer to be partially open. So the design of the solenoid is really not different, it's the way it's controlled. If you had this solenoid on the bench and hook battery voltage to it, it would just open, and if you take battery voltage away, it would just close. But the way the computer controls this particular solenoid is using something called duty cycle. Now, the duty cycle is a percentage of on time. So for example, if this turned on for 1 millisecond, off for 1 millisecond, on for 1 millisecond, off for 1 millisecond, that would be a 50% duty cycle. If it was on for 3, off for 1, that would be 75%. If it were on for 1 and off for 3, that would be 25%. So what I'll do now is I'm using the Autel scan tool. I'm going to increase the duty cycle of the exhaust gas vacuum regulator. And I don't know if you'll be able to tell, but as the EGR valve opens further and further, the engine will run rougher until probably it will eventually stall. So let's give that a shot. Okay, I'm starting to hear a little roughness in the engine at 40%. Even more so at 50. 60, it's idling pretty rough. Well, surprisingly, it's able to handle 90%. Even 100%, but it is not running well. Here's another example of controlling a solenoid more than just turning it on and off. Fuel pulse width 1 and fuel pulse width 2, notice, are measured in milliseconds. So what we're looking at here is every time that fuel injector opens, how long does it stay open before it closes again? Notice the engine is at essentially idle speed. We're at about 880 RPM. If I go increase the idle speed, increase the load on the engine, we should see the injector pulse width numbers get bigger because the computer needs to deliver more fuel. Since the fuel pressure is pretty much fixed, the only way to deliver more fuel to the engine under higher loads is to leave the injectors open longer each time they open. I'm going to jump in the car, step on the brake, give it a little gas, and try to put a little bit of a load on the engine. What you saw is the numbers got quite a bit bigger there as the engine required more fuel. You can include in your report the numbers you saw there, what the numbers are at idle, what they were under a little bit of a load, and what they were when you heard the tires squealing. I've removed the shield so we can see the fuel injectors on this Crown Vic. Here's the number 1 fuel injector, the electrical connector for it. I'm just going to disconnect that a minute. And there's a red wire and a tan wire. With the key on, see the red wire is hot. and the tan wire is not. So this red wire goes to all 8 fuel injectors, powers them up when the key's on. It's up to the PCM to ground the other wire in order to open the injector. How do we know if the PCM's doing that? We can use a Noid light. Noid light just basically replaces the fuel injector in the vehicle and allows us to see that it's getting both power and ground. Now when I start the vehicle, this is going to start to flash. I don't know if the camera is going to be able to keep up with the flash rate of this injector. So just get it where you can see it well, and we'll see what happens. You may be able to see that on the video, not sure if you can hear me over the engine, but it's flashing. Could be one pulse essentially for every time that injector needs to fire. So every intake stroke you're going to see another pulse. I have this oscilloscope set up and connected to the number 1 fuel injector. It's connected to the negative wire, the wire that's grounded by the PCM. So right now, I have the scale set to 5 volts per division, so 5, 10, 15, and the time, it's about 5 milliseconds for each block. Hooked to DC, we're looking at channel 1, which is what I'm plugged into. And so when I turn the key on, we should see something happen on the screen here. What I'm going to do is let me focus in a little bit more just on that screen. And I'll turn the key on. So we can see now it's reading 5, 10, just over 12 volts DC. So we're on the negative side, but it's not grounded, so we're seeing the voltage that's supplied to the injector. Whenever it's grounded, that should be pulled down to 0. So I'll start the vehicle. Might be a little hard to see through the camera. We'll see if we can find the pulse width or where the injector is actually turned on. What we're looking at for on time is when it's pulled down to 0 here. Kind of hard to get it to sit still because the engine RPM is not perfectly stable, but it is a little more than half a block, I think, and each block is 5 milliseconds. See if I can make it stand still a minute. Another interesting thing is every time this injector turns off, there's a big spike. Anytime you energize an electromagnetic coil and a magnetic field builds up around it, when you de-energize it, you see that big spike. A lot of devices have something in place like a clamping diode or a resistor that's designed to keep that spike from hitting the computer. It can be several hundred volts. Right now it's going off the top of the screen. I think that injector on time has settled down to about half a block, so that would be a little more than 2.5 milliseconds, 2.6. I don't remember what we saw on the scan tool, but it would be about the same. It should be about the same. So right here is where it's sitting at whatever battery voltage is with the car running. Looks like about 15 volts. And every time the computer pulls that circuit to grounds it in order to make the injector fire, you see the voltage sits down here at 0. And then when it ungrounds it, there's a big spike comes out of it. Now that we've looked at things on the bench and out in the shop, hopefully you have a lot better understanding of how solenoids work. So we saw that solenoids are basically an electromagnet with a movable core, and when you apply power to it, it can open and close a valve, it can make something move, it can let vacuum through, it can let air pressure through, it can let gasoline, transmission fluid, whatever flow wants to be controlled, they can do with a solenoid. Then we saw that, the EGR vacuum regulator, for example, instead of just on or just off, could be a percentage on-off. That's called duty cycle. So we rapidly turn the power on and off to it, and that controls just how much current's flowing through it, how far it actually opens. The other thing was the fuel injectors, we use something called pulse width modulation. So pulse width modulation is not really a percentage because off time doesn't matter. It only matters how long it's energized. The longer it's energized, the more flows through it. This is typical for fuel injectors, a lot of pressure control solenoids, automatic transmissions, pulse width modulated. It's just a way of controlling how much flow. So the longer the pulse width, the more flow. And the example we used was a fuel injector where you saw at idle speed we had a very small pulse width, couple milliseconds, and I think it hit probably somewhere near 14 if I remember right when we hit the gas and the vehicle needed more fuel. So after watching this video, you can go back watch as many times as you want to get the numbers you need. Write your report, put in all those numbers, put in what the milliseconds were on the injectors. Tell me what happened when we increased the duty cycle on that EGR vacuum regulator. Talk to me about what happened on the bench when we energized that vacuum solenoid and when we energized the fuel injector. Write up your report and send it in. Please use email. When you send them through Blackboard, for some reason I cannot get them. Until the next lab or until a lecture, stay healthy, stay safe, and who knows, maybe we'll see you by the end of the semester.